I'm calling my latest project the video call Interruptibility Status Indicator, or VISI for short, a device to show people around you if you're Zooming or FaceTiming, and whether you're available to chat. Based around a Raspberry Pi Pico, buttons control the traffic light colours from an RGB LED, and a backlit LCD text display clearly shows if you're busy or not, even to people who can't see from your laptop screen that you're on a call. Now this is really part 3 of the project. In 2 previous videos I worked out how to get my traffic light colours and how to control them with buttons, but it's really only with the addition of the text display screen that I get to a fully functioning device. I've made a little playlist of all 3 videos, which you can find on the link above, but I'm starting this one by adding the screen to what I've already got, so you may want to go back and see how I got this far before carrying on. The screen I'm using is a 32-character LCD display with an RGB backlight, which cost me less than £15. Now this connects with a thing called I2C or I2C, standing for Integrated Circuit. This is new to me, so I'm going to be doing quite a bit of learning along the way. And first of all, with sockets rather than plugs at the end of the cables, work out a way of connecting it to the breadboard. For this I'm going to use some spare resistors, or rather the wire either side of the resistor, being the right gauge for the breadboard, and just snug enough not to fall out of the socket. There's plenty of wire left either side of the resistors, so they won't go to waste. Now we need to work out where they're going to plug in, and without any paper documentation we're going to need to head to the internet. And DuckDuckGoing, the product name, takes us straight to the Waveshare website. Here on the product page we get all the details, but this is pretty much what we knew when we bought it, although scrolling down we do find a wiring diagram. But let's skip past that for now, because what we really want is right at the bottom here. A link to all the documentation held on the Waveshare wiki, which will not only give us the wiring for our particular board, but also any downloads we're going to need. The first thing to notice is our colours don't seem to match, but it isn't rocket science to work out that teal and purple are the same as the red and black, connecting to the 3.3 volts and the ground on the Pico, as they're clearly labelled next door to the plug. Blue and yellow are the same as on the wiki. These are our I2C data cables, and we just need to count in the number of holes on the breadboard to get the yellow one in the right place. The blue one goes next door. And that's the wiring complete. Now we're going to need some software to process that data, the I2C driver. And just below the wiring diagram on the wiki is the link to where we can find that. This is the bit we need, although it is rather buried in some stuff that I don't fully understand. And all I need to do is copy and paste it into a new tab on my browser, and it will download the zip file as soon as I hit return. Now we've got to get the contents of that file onto our Pico, first of all connecting it to our host computer, simply plugging in the micro USB cable. But after that it becomes a little bit more complicated. We can find our zip file easily enough in our downloads folder, but to extract the contents we need to right click on our mouse and scroll down to extract here. We can't just double click. And here's the folder we've extracted, and inside that are all the files we need for our Pico, and a load that we don't. And as we've already got MicroPython installed, we won't need the RP2 file either. Now we need to get the 3 files we do want onto our Pico, remembering that that won't be listed in our folder directory, and we have to open something like Thonny to see the files. And here, in the bottom left-hand pane, are the various Python programs I've accrued getting this far in the project. In the pane above are the folders of the host computer, my Raspberry Pi 3B. And I need to navigate through the home folder to where the downloads are, working through the folder structure until we get to the Pico and the Python folder inside. And here are those 3 files, the ones we saw on the desktop. And to get them into the pane below, the one for the Pico, we need to right-click and select Upload To from the drop-down. And here they are, listed alphabetically in amongst my other programs. Before we look at the new files, let's remind ourselves what we've already got by opening main.py. That's the latest version of the program from part 2 of the videos. Here we have pulse width modulation controlling the colour of the LED, which changes when the buttons are pressed, switching between the traffic light colours and turning off with a press of the black button. It's to this code that we want to add the controls for the screen, so let's see what we've got in those downloads. First, let's have a look at RGB1620. This is the screen driver itself. There are bits we can recognise, but mostly it seems like a foreign language. It is of course just a bit of Python, and it really doesn't matter if we don't know what each line does. We can treat it much like a module from one of the libraries, which I'm guessing is a similar kind of deal. But as we can't see those, we don't even begin to think about how they do what they do. Now let's have a look at those other two files, starting with Choose Color. And right at the top of the program, we can see it importing that RGB1602 file in exactly the same way as other modules from the MicroPython libraries. And here's what the program does. We've got a classic Hello World message spelled out on the LCD while the RGB backlight changes color, which isn't a million miles away from what we want it to do. So there's definitely stuff we can use from that. The second program is rather enigmatically called discoloration. What it actually does is fade through a sequence of backlight colors. That undoubtedly shows off the capabilities of the screen, but is perhaps going to be less directly useful for us. So let's close that down, along with RGB1602, leaving just Choose Color and our main.py program, to which, having made a backup copy first, I'm going to add the bits we need, copying and pasting from Choose Color, starting with the RGB1602 import. Switching back to Choose Color, we can see two more libraries. We're already importing the bit of time that we need, the sleep module, and I'm pretty sure we don't need the math. That appears to only be required for the discoloration program. But I am going to copy across this chunk, even though I'm not entirely sure what all of it does, in particular those color values. Then with the basic setup copied across, let's have a look at what the other bits do. Running the program shows it cycling through 9 colors. And we can see each of those defined in the code, with the individual values for the red, green and blue, using a number between 0 and 255. Now this is a fairly conventional way of expressing RGB colours, and this is the 5th one in the cycle, the one that's closest to the kind of orange we're after. So let's copy that and paste it into main. I'm conscious that that gives us two different ways of defining our colour mixes, one for the screen backlight and another for our RGB LED. I'm assuming the screen drivers use PWM somewhere along the line, making a calculation that simplifies the format. And while it may not be that elegant to have two different ways of defining our RGB mixes, I think we can live with that. The last two in the Choose Color sequence will do nicely as a starting point for our red and green, but like with the pulse width modulation for our RGB LED, we'll want to tweak those values a bit. But before we get to that, let's give them some names that are slightly more appropriate to our program. My use of upper and lower case is slightly random, but it does help to differentiate between the groups of definitions. And when I've got my red, orange and green, I just need one more, for when the backlight's off. And just like the naming of the buttons, I'm using K for black instead of B, as we don't want it to get confused with blue, and values of 0 for R, G and B. Now let's switch back to Choose Color and scroll down the code for the next bit, which sets the text for the screen, one line at a time. We could ignore some of that slightly random narrative in grey, that's obviously a mistake, and copy the first line, which sets the cursor. What we're after is a different message depending on our availability status, so the code that generates the text will need to go into each of the if statements. And having freed up a little bit of space, I'm just adding that set cursor instruction. Flicking back to Choose Color, I can highlight and copy the bit which tells it what to say, and paste it in. We'll be changing the words later. Then back to Choose Color for the next bit. I could, of course, have copied the whole chunk in one go, but it suits my learning process to do it line by line, so I really understand what's going on, noticing things like the coordinates for the cursor, which this time is still on the left, but one row down, and that's where the second line of copy will start. Now to change the words. Our red button is for when we shouldn't be disturbed, so it needs to say that we're on a call, and now is not a good time to chat. The exact wording is quite tricky. After all, we've only got 16 characters per line, including spaces and punctuation, and the line breaks are going to be important too. This is what I settled for, pithy and to the point, without, hopefully, seeming rude. Now on to the other buttons, and for these I am going to copy the entire chunk, and paste it in the same position for each, spacing out the lines of code so not only do they look nice, but they're easily understood, and I'll remember what's going on when I come to add the next bit. Our amber status is for when we are on a call but perhaps not participating fully, probably on mute, and able to answer simple questions, but not available for a full-blown conversation. Green is for when you're more of an observer, perhaps just watching a presentation or even a video, and may actually welcome an interruption. Or you've just got your headphones on and are listening to music while you work, happy to press pause and have a bit of a chin wag. Time to put it to the test, and it's here that my sole reliance on the demo code comes unstuck. When the message changes, some of the letters at the end of the previous text are still on the screen, so I must be missing some key element. I'm indebted to Christopher Barnett's Understanding Computers YouTube channel for the answer, which is to add a line clearing the screen before adding the new text. This wasn't in either of the demo programs because the text didn't change, only the colour of the backlight. But as we're going to be changing both, we're going to need to add that line to each of the button presses, so the previous text is cleared away before adding the new. And with our status messaging now sorted, we can turn our attention to the backlight. Returning to the Choose Colour program, we can scroll down to find one of the lines of code that sets the colour. There are 9 of these, one for each in the sequence, but we'll only need to copy one, and we can take that over to main.py and make a little bit of space to paste it in. At the moment that's referencing one of the colours from Choose Colour, so we'll need to change that to one of the ones that we created earlier, in the first instance, the red one. Copying R_LCD, I can now paste it into the code, in place of RGB1. Now I'm not entirely sure why, but this seems to need to be done 3 times. My best guess is something to do with the separate RG and B values, but if anyone knows for sure, perhaps pop it in the comments. Before we go to the next one, let's try out the red. And now, a press of the button changes both the backlight and the text, as well as the colour of the RGB LED, which you can't see because it's off screen. With that working correctly, we can go on to the orange and green backlight colours, copying the code for red and pasting it into a similar position for orange. And with my naming convention, all we need to do is change the R's to O's in each of the 3 occurrences, and then exactly the same for green, just changing the first letters in all of the 3 places. Now when we run the program, a press of each button brings up the right message and a suitable corresponding backlight colour, red for busy, green for free to chat. Just one last option for the backlight remains to be programmed, and that's for the black button, which is there to turn everything off. And I can use exactly the same bit of code, but with K's instead of R's, setting the brightness of R, G and B to 0. And with that we've got a fully functioning status indicator, a press of each coloured button, changing the message on the screen, as well as the colour of the LED and the backlight. And when we're finished with it, we can turn it all off. Now I want to do a bit of finessing, in particular tweaking those backlight colours, which I'm not completely happy with, and as we've seen can make the text hard to read. We did a similar thing with PWM and our LED, and like that we can do a bit of trial and error, adjusting the proportions of each colour, compensating for the overbrightness of the green, and softening each one with small amounts of the minority colours. And the great thing is we can test them straight away, so if we do over-egg the values, it's easy to revert to what we had before. For this stage of the proceedings, I've just got a couple of minor niggles to sort out. First of all, when my backlight turns off, I've still actually got the text on the screen. It's faint, but we can see it, but really easily solved with our LCD.clear. Then one final little tweak, which is to add a tiny pause after clearing the screen and before putting the new text up, just for a smoother transition. So this is what we've got. We've got buttons that change the colour of the LED, the text on the screen, and the backlight colour. But while it's fully operational, it's clearly far too unwieldy to use even as a working prototype. So in this second half of the video, I'm going to set about turning it into something much more functional. And I'm going to start by moving my Pico to a much smaller breadboard, prising it up gently so I don't bend any of the pins. I'm going to be replicating most of the other components, so I'm going to leave those and the wiring in place, so I don't forget what that looked like. And here's our new breadboard, which I've carefully chosen to provide enough columns and rows for our requirements whilst being as small as possible. Conversely, I've opted for a much bigger LED, giving us an improved 360-degree visibility, and I've chosen the appropriately named Squid from Monk Makes. This has the same 4 connectors as we had before, but not just with added wires. It also has built-in resistors, which will tidy things up no end. However, like our screen, the jumper cables only come with sockets, not plugs. So once again, I'm going to sacrifice the ends of some of my resistors, so I can plug them into the breadboard. And obviously there's more than enough left, so I'll still be able to use them, but they won't be needed for this project. Now, with the simplified wiring, I can plug the LED directly into my breadboard, with each colour-coded cable corresponding to the same pins that I used before. Now we come to our buttons, or should I say tactile switches, and I've got something up my sleeve that's going to simplify that wiring. What I'm going to do is plug the diagonally opposite connectors of each button directly into the breadboard, and I'll be using that common rail along its length to connect one side of each button to the 3.3 volt power supply. And I'm just making myself a little jumper out of a spare resistor wire, bridging between that outer row on the breadboard and pin 36 on the Pico. The other connector on each button will plug directly into whichever column on the breadboard corresponds to its assigned input pin. The other connectors I'll need to snip off, otherwise they'll just short circuit across the button. Fortunately, I've got some really sharp track cutters from the modelling side of my interests, which makes easy work of it. Now I can push the button into the breadboard, one connector in the outer rail, the other next to the input pin. But first, I need to work out which pins to use. With the wired version, I could choose pretty much any, but with my direct connections, the choice is much more limited, and clearly requires a bit of planning. The spacing of the button pins means I need to skip a row on the breadboard. I can still use pins 16 and 17 for my red and orange, but the orange button itself is going to get in the way of pin 18. So I'll need to use pin 19 for the green, with the connection to the 3.3 volt feed 2 steps to the right. It would be nice to put the black button directly next door, but I've only got a choice between one of the ground pins and that run, so I'm going to have to leave a gap and go for pin 22, and that's really not a big deal. But my new pin locations have caused a new problem, as the black button will block the pin I'm using for my blue LED, but not a massive issue, and I can just switch to 4 adjacent pins with the ground in the middle on the other side of the board. I'll just have to change the numbers in the code later. I'll have to do the same for some of the buttons, but not the red. That will stay the same with pin 16. And having worked out which legs I'm going to be keeping, I can snip off the others, leaving one to connect to the 3.3 volts via that outer rail and the other to pin 16. It's here that we hit a minor problem. With only half of the pins inserted into the breadboard, our button's a bit wobbly, so we're going to need something to hold them in place. And for now, a strip of double-sided sticky tape should do the job. Later on I can glue them down, but I want to make sure everything is in the right place first. And with my sticky strip running between the holes in the breadboard, I can start assembly. Red button first, and then on to the orange, which will be using pin 17. This means my diagonal will go the other way, so I need to be careful to snip off the right legs. Although, even if I had got it wrong, actually I could have used pin 18 instead. But I hadn't spotted that when drawing up my plan. Then the button can be put in place, with the remaining legs inserted into the appropriate holes, and pushed down on my sticky tape. And onto the green one, using exactly the same procedure, until all 3 status indicator buttons are in place. But we mustn't forget the black button, the one that turns everything off, and as its role is slightly different, in the end I'm not that bothered that it's a bit separate. So let's quickly recap. Red and orange are using pins 16 and 17, green 19 and black 22, with the other terminal of all 4 buttons sharing the common connection to the 3.3 volts. Now we can set about moving our screen across to the new board, starting simply enough with our purple ground wire, just counting in the number of holes to the right position. And then for our green positive. Now its hole is actually blocked by my little jumper, but not a problem. It can actually go anywhere along that outer row. But we are going to have an issue when it comes to our screen data cables. The yellow one's fine, that can slot in where it was before. But our new position for the LED is in the way of where the blue should go. I'm sure there's a way of redefining the pin for the I2C, but it's just as easy to move our LED, finding the next set of 4 clustered around the square padded ground pin. Then with its home vacated, our blue wire can go back into its old position. But with everything else shunted around, we now need to get into the code and change some of the numbers. After a bit of a detour, our RGB LED finally ended up on pins 9, 10 and 11. The red and orange buttons remain unchanged on pins 16 and 17, but the green moves on 1 to 19, and the black is now on 22. And with all the numbers updated, we can run our program and put it to the test. A quick press of the black button will turn off the default backlight, and red's looking great. But with the squid's built-in resistor, the green is way too bright, which is also affecting the PWM colour mix of our orange. Back in the fully wired version, I'd address this by using a larger value resistor for the green element of the RGB, compensating for its brightness. But that was all before I was using pulse width modulation, and now with that I've got much more control over my colour balances, both for the green on its own and the mix for the amber. In a previous video I look at PWM in some detail, but for our purposes here, it's enough to remember that the brightness of each of the components is set by a value somewhere between 0 and 65535. And by experimenting with the combination of those numbers, I can adjust the colour mix of my amber until I've got something I'm happy with. Now we want to get that green right, and tweaking the numbers in the software is so much easier than fiddling about with different resistor values, and perhaps best of all, I can test them straight away, finally settling on a figure that's about half of maximum brightness for the green, with a little bit of blue just to soften it. Then, completely happy with all three of my traffic light colours, I can save this version of the program to be the one that starts automatically when the Pico powers up. And having backed up the previous version, I can delete that safely and replace it with the new one, simply saving as main.py. Now we can close all of our programs, exit Thonny, and unplug our Pico. Now, while our new compact version is a much more practical size than our initial prototype, we are going to need to find a way of holding the two parts together and to mount it on the top of our laptop screen. And where else would I turn other than Lego Technic? And I've got myself some angle brackets, which seemed a good place to start. Lego is the obvious go-to. It's easy to put together and easy to take apart again if something doesn't work out first time round. And I'm going in with very much that attitude in mind, starting with some simple brackets that will hang over the top of the laptop screen, with the breadboard on top and the display screen in front. Eventually it's all going to be held together with some double-sided sticky pads, but while I'm experimenting I'll need something a bit less permanent, and some blobs of blue tack should be fine, with just enough stick for a quick tryout, and enough squish to get round some of those components sticking out the back of the screen. It's all a bit wobbly at the moment, but it only needs to be good enough to hold together for a while, and attaching the breadboard on top should stabilise it a bit, but I will have to handle it gently, and definitely not drop it on the way to the laptop screen. As a first attempt it's actually not that bad, particularly when the screen is bolt upright, but less good when the screen leans forward, which it normally will. So here's my Mark II bracket, with some added bits from a Technic breakdown truck. I factored in the screen angle, and it's even got a bit of adjustability. But we'll only really know how well it works when it's assembled, and so back to the blue tack, first attaching the display screen, pressing it firmly on the front of the brackets, and then the breadboard on top, getting it the right way round this time, with the buttons at the back and the LED at the front. Now for the moment of truth, let's get it up on the screen and see how well it works. And for a prototype, I'm pretty pleased with that. Before I commit to the sticky pads, there's a couple of improvements I think I can make. These extra bits on each bracket will help support the screen, and this cross brace between them will make the whole thing more sturdy, and with the right number of spacers, keep them exactly the right distance apart, which will help massively during assembly. Even my dry run just about holds together without the sticky fixers. So confident it is going to work, I can start sticking it together, beginning with the screen. With all the bits and bobs sticking out the back of the circuit board, I reckon I'm going to need a double thickness sandwich to ensure a really good connection to the brackets. And you can see how those orange steps really help line it up before squeezing it in position. And that cross brace keeps it all square. We're no longer reliant on the breadboard itself for the structural stability. That can just stick on top, making sure it lines up, both with the back of the screen and with the brackets themselves. And with the final squish of the sticky foam pads, we can lift it up and really try it out. Plugging in the USB cable that's going to provide power from one of the laptop's ports, automatically launching main.py, and we're fully operational, able to tell people when we're on a call, when we're free to chat, and when we aren't. We've even got a bit of adjustability, so our display is facing directly forward over a range of screen angles, and our breadboard and buttons horizontal, for ease of use. Now the next thing to do is to package up my video call interruptibility status indicator into something a little more elegant, but that'll have to wait for another day, and perhaps another video.